One very popular method of frequency compensation is so-called Miller compensation. Basically, it is a form of pole splitting in which the coupling between um, two resonators or two poles is changed. And although it's a very popular method, it is definitely not as good as phantom zero compensation. And it will be clearly shown in this example of the antenna amplifier, but it's almost always valid. So, pole splitting. Here we can see an implementation of pole splitting in the second stage. The first stage, the CS stage, is shorted in the case as I have shown, which means that we cannot do any pole splitting there. We would effectively just put a capacitor in parallel with the input. But in the second stage, there is already a certain amount of pole splitting because we have seen that the non-dominant pole was calculated to be 450 megahertz, but according to SliCap, including the CGD of the second stage, it was at 1.2 gigahertz, so there was already a amount of pole splitting, and this product of the poles was still enough to get the bandwidth of 1.4, 1.5 gigahertz. So by adding externally a capacitor to CGD, we can increase this pole splitting. Now, maybe you remember in the quiescent operating point that the GM of the second stage is about 25 milliamps per volt, and the load resistance of the second stage is 2 times the characteristic impedance, which is 100 ohm. So 25 milliamps per volt times 100 ohm is a voltage gain of 2.5, which makes, according to the Miller effect, that you could place C compensation a factor 3.5 its value in parallel with the input. So you say it's not very effective since there is a very low voltage gain. That means if you want to have a considerable splitting, C compensation cannot be very small. And by inserting it then, it will also affect the product of the poles. Only if the charge on the compensation capacitor will be, or if the value, of the compensation capacitor is much smaller than both the load capacitance and the input capacitance of the CMOS stage, then there will be almost no effect on the product of the poles. But in this case, we can already say because of the low voltage gain in the output stage, we are going to expect some effect on the bandwidth. So the sum of poles must be increased, and we must increase it to minus the square root of 2 times the bandwidth to have a maximally flat magnitude characteristic. But as I told you, there's a low voltage gain in the second stage, requires a large compensation capacitance, and we have expected bandwidth reductions. So dual stage pole splitting .pi will give us the answer to the situation. And I will make it active here and run the thing. Okay, so I didn't plot any Bode plot here, and I didn't calculate. Oh, let's go to the file, otherwise it doesn't make any sense to you. I didn't calculate the, as in the previous, the bandwidth and the poles and calculate the compensation capacitor. I could have done so, but of course, while compensating, I expect to reduce the bandwidth. That's because of my expectations I've shown you in the previous sheet. So what I'm just going to do is I'm just inserting a capacitor and stepping its value from 0 to 1 PF. 1 PF is about equal to CGS of the stage. So, and then see what happens with the sum of the poles. But remember, the final result is I want to have the poles in 45 degrees. So a real part and an imaginary part. This should be equal. Then I have a maximally flat magnitude characteristic. Now you might say this is not very scientific, but let's say basically the most important thing we are trying to teach you here is that you can evaluate various methods. Sometimes things just get too complicated to make hand calculations, and you just you use a numeric tool to see the result if you are stepping some value. So the consideration here is that I am expecting a bandwidth reduction because of the low voltage gain in the output stage, and for that reason I need probably a large capacitor. I will have bandwidth reduction and a less effective let's say frequency compensation than the phantom zero at the input with the resistor, which is still the best one we have met up to now. Now look at the root locus when I'm stepping this capacitor, and look at the root locus when I'm putting it on equal scale, so you can really see the 45 degrees. I can get them under 45 degrees, but you see they're not moving over a circle. If they were moving over a circle, the poles, then it would mean that my bandwidth remains the same. But you see they're almost going in a straight line down, which means that the distance to the origin decreases with it, and that is the bandwidth. So the bandwidth decreases while compensating, and at the end I have 700 megahertz left of the 1.4 gigahertz I initially started with. Of course, since we need only 30 megahertz, you might say this is not a problem here. But maybe I still want to have more loop gain at higher frequencies because of intermodulation products, because of out-of-band EMI, etc. This is to be dealt with next time. But I see with this Miller compensation in this way, so with this pole splitting, I cannot really get a compensation independent from bandwidth reduction. So we can see the sorry, I'm clicking the wrong button. We can see the other one, HTML file. Pole splitting. And here is the circuit I used for the pole splitting with LT-Spice. So you see, I just added a compensation capacitor here and I'm stepping it. And the nice thing is I don't have to do anything about biasing. You can just do this with SliCap. Don't think about the biasing. That will be the next stage. It simulates with small signal equivalent diagrams. The output we have already seen, and the most important plot, but now a little bit larger, is this one, in which you see that while increasing the capacitance, the bandwidth is strongly reduced, effectively by a factor 2. So for this antenna amplifier with this low voltage gain in the output stage, this is definitely not an issue, not an optimum method. And I expect also a large variation if I'm going to drive the load, because if the output stage is going to deliver more current, its GM will probably rise. And then the poles will move with because the bandwidth will then increase and will move with the current delivered. So this is the pole split technique with what is usually called Miller compensation.